Hello students, this is our last lecture, our third lecture, excuse me, on chapter 10, free radical reactions. We're going to introduce a new free radical reaction. It's addition of HBr, hydrobromic acid, to alkene pi bonds. This is going to allow us to make something that we could not make in our previous examples. We're going to be able to put a bromine at the end position, the primary position right here. This is called anti-Markovnikov addition to alkenes. Unfortunately, we haven't seen Markovnikov addition yet. That's later. But this goes on in a different way than is possible. We could put a bromine at the internal position, which is called Markovnikov addition. But that'll come later. So this is also a free radical reaction, and it occurs in a sequence of steps similar to what we just did. There's an initiation. Okay, this initiation is a little more complicated because it involves two steps, but it gets things going. And then there's the guts of the reaction, the main part, which is propagation, where we do two steps back and forth to make the product that we're looking for. Okay, so initiation's kind of rare, and then there'll also be a termination at the end, just as in our other examples. So if we look at the conditions, we can see how it's a little different. Remember, in the other free radical substitution reaction, we had bromine, Br2, diatomic bromine molecule, and we use light. So in this case, we're using HBr, hydrobromic acid, and we're using a peroxide. Okay, the peroxide has a very weak bond in this oxygen-oxygen bond that we're looking at right here. And that's going to break homolytically when we shine in light. Again, H nu represents light. Okay, and when it's all over, we'll have this compound that we could not make before, which we want, and then we'll have sort of a complete set of bromoalkanes. Okay, so initiation is we have a tiny little bit of this peroxide, and we're going to shine in light. Since this is such a weak bond, it's around 40 or so, thereabouts, we're going to cleave it homolytically. Notice half-headed arrows, or what we call fish hook arrows, will split these two. Okay, now this free radical needs to find something to react with. It has two choices. It has the alkene and it has the HBr. So it's going to choose the H off of the Br because that makes a nice strong OH bond. Okay, and then that will leave us behind with a bromine atom. And this is what we need to get the reaction started. We need this bromine atom. So this is kind of a throwaway. Remember, we just have a little bit of this peroxide. It starts off this reaction, and then we have this bromine atom, or bromine free radical. Okay, so overall, this is a very favorable reaction. The bond energy of the OH right here is very, very strong. So that's going to be downhill about 110 here. And we're breaking an HBr bond, which is also a pretty strong bond. That's 88. But overall, this is very favorable. But again, this is just sort of a rare reaction to get things started. Now, when we come down here to see how the reaction actually proceeds, the bromine has a choice here. It has two carbons it could react with. It could take an electron with this carbon and make a bond, or it could take an electron with this carbon and make a bond. Wherever it does that, the other atom will become a free radical. So if we join up with the N position right here, we make the free radical at the secondary position. If we joined up with the carbon here, the free radical would have been at the primary position. And if you think back, secondary free radicals are more stable than primary free radicals. So by picking the N position here, it's making the more stable intermediate that we're looking at over here. Okay, so we're saying that the pi bond, carbon-carbon pi bond energy is pretty weak. I have it listed as 63 here. The carbon-bromine bond isn't super strong either, but it's stronger than that. So it's actually an exothermic reaction to do that. So that's a favorable reaction. Now, once we do that, we have a carbon free radical. So the carbon free radical is going to kind of choose what the peroxide free, oxygen free radical up here did. It's going to come over and it's going to steal the hydrogen away from HBr. Okay, and that'll give us the completion of our molecule here. Okay, that'll finish this off and give us this bromoalkane with the bromine at the end. The bromine atom now is available to come back up and do the whole thing all over again. And so here we are in this chain reaction. Step 1, step 2. Also, this is an exothermic reaction. Okay, we're breaking HBr. That's about 88 plus, but we're making a CH bond, which is a strong bond. So that's going to be someplace in the 90s, depending on what kind of CH bond we make. Okay, So this is a favorable reaction, and now we have to add it to our tool chest of reactions. Now this could be a little bit harder. If you look back up to this example, this is a pretty easy example. There's nothing complicated here. Got 2 hydrogens on the end. When I get over here, there's no chiral centers. There's no cis or trans. There's all kinds of possibilities that could exist, but do not exist on this one. So I sort of called this one the easiest example. Now all the steps are going to be basically the same. But if we started off with a molecule like this, this is a more complicated looking molecule. For one thing, if I look at each of the carbons here, they have different groups on them. Here's a deuterium, here's a phenyl. This carbon has a deuterium, and here's a hydrogen. So that's not entirely by accident. That was on purpose so that we can see some of the complexity that's involved in this. Now remember that bromine chooses the less substituted position, which would be here. So if I put a bromine here, I would have 4 different groups, and this would be a chiral center. And then the H is going to go on the other one, and you'll see why I put a D here now. By putting a deuterium here, when I add the H, this will also be a chiral center. So in fact, by adding HBr to this alkene, I'll be making 2 chiral centers. And if we have 2 chiral centers, remember we have 2 to the 2 possible stereoisomers. So 2 to the 2 is 4. That means we would have 4 possible stereoisomers. And that's going to happen here because this is a flat structure and we can add from the top or the bottom. So if we come over here, I've written them all out. You can double check and see if I did this right. Let me see, that would be 1, 2. Yep, okay. So anyway, you can double check that looks correct right here. Bromine, carbon, deuterium, R. And so you see SR, and then down the line you see RS. So we know that these are enantiomers. But also we can make RR, and the mirror image would be SS, and we can see that here. So these are enantiomers. So in addition to the enantiomer combinations, we also have SR and RR. These are diastereomers. SR and SS diastereomers. So we have all kinds of possibilities here. What we do not have is any meso compound, because there's no mirror plane that we can cut through the middle of this molecule. Okay, now the mechanism is going to be exactly the same. We're going to blow apart this peroxide bond, this weak bond right here. Okay, it gives us an oxygen-free radical that snags a hydrogen atom. Okay, makes an OH bond right there. So it looks like I changed this from, I did have R up here. I should have an R. But in any case, that'll give us an OH bond, and then the bromine atom. So the bromine atom now will come over and add, and it will add to the end that gives us the most stable free radical, and that'll be the secondary free radical. Remember, this is an electron-deficient center, and so more inductive groups donating in help stabilize it, so that's better. Now this carbon free radical will come down and pick an H off of the HBr, and that will complete our molecule. But as we go through here, notice what happens. This is a flat structure, so the bromine has no preference really for the top or the bottom. It could add to both. All right. So when it adds to both, we're generating both possible absolute configurations at this chiral center. So if it adds to the top, we're getting R, and if it adds to the bottom, we're getting S. And so this is what's going to carry forth down here. Okay, so we'll have both of those possibilities. Notice as I have them drawn here. Bromine on the top, bromine on the bottom. Now when this picks off an H, the free radical carbon is also flat. And so that means once again we will be able to add from the top or the bottom. Okay, so if I add here on the top, it would look like that. And if I add here on the bottom, it would look like that. And that's going to change the absolute configuration of this second chiral center. And over here, with the bromine on the bottom, I could add the H from the top or the bottom. So when you come down here, you see all the possibilities that we mentioned up here. Okay, so we get SR, and we get RR, and we get SS, and we get RS. So this is definitely a harder example than the first example, because the first example had no chiral centers, nothing really to worry about. Okay, now this could be even harder. First off, here's the enantiomers. Remember, SR and RS, those would be enantiomers. SR and RS, A and D, and B and C would be enantiomers. And all the other possible combinations are diastereomers. Okay. Now I call this hardest. Okay, now why is this the hardest one? Well, it's not the start of the reaction, because the start of the reaction is going to be pretty much the same. These H's should really be R's, so It's not a big deal, but it's a little bit of an error here. So I have the oxygen free radical grabs an H, so that gives us this OH bond and our bromine atom. So in every mechanism that I've shown you so far, that's always been the same. Now the bromine atom has a double bond to react with, so it can add, and it will add in this unsymmetrical way that we mentioned before. It's going to make the most stable free radical. Now this one's a little different because I don't have a terminal alkene. Okay, so this is only substituted one place here, but it's substituted two places here. So the choice will be the bromine could add to this position and make a tertiary free radical, or it could add to the more substituted position and make a secondary free radical. So again, a more substituted free radical is more stable because it has a greater inductive effect to help stabilize the electron deficient free radical. So it's going to add to the end out here. But since this is flat, it can add to the top or the bottom. That was just like in our previous problem. So I have it on the top, I have it on the bottom. But what's different here is our molecule came with a chiral center already present. Okay? So the interaction between these two possibilities is really going to be like diastereomers. So they would not be exactly equal, but we're not going to worry about that. We'll just say that it can add from the top or the bottom, approximately equal. And then once we get the carbon-free radical, that carbon-free radical can come over and grab an H atom and complete our molecule, give us a neutral molecule. And again, since the free radical is flat, it's possible to add from the top, okay, or the bottom. But that'll be true for all the possibilities where the bromine added to the top or the bottom. And so that, once again, that's going to lead to four possibilities. If we neglect the S and the starting structure that does not change, this never changes in the whole reaction. Okay, it's just a double bond that's changing. Then we still have RR and RS and SR and SS. But in all of these cases, we have an S that's sitting over here that never changes. So we have no enantiomers this time. Okay? Because S is always the same. And to be an enantiomer, it has to be a different mirror image. So what we have are all diastereomers. Okay? All four of these are diastereomers. We have 3 chiral centers, so it would be possible to have up to 2 to the 3 or 8 stereoisomers, except we never changed S. 4 of those stereoisomers would have S being equal to R, and we never do that in this reaction. Okay? So this would be a complicated example of all the different outcomes that could happen. Okay, it's definitely a more challenging reaction. Of course, termination is just a combination of any 2 radicals, and you would want this to be a pretty stable product. Bromine and bromine really wouldn't work. Okay, so now things have expanded quite a bit. This is kind of a review of the ones that we just looked at. Here's the starting hydrocarbons that I'm giving you: methane, ethane, propane, 2-methylpropane, cyclohexane. We're looking at this sp3 part up here. So this is methylbenzene, or also called toluene. And then we're looking at the sp3 parts here. Notice there's 2 different carbons. So this would be ethylbenzene. Now the way we functionalize these guys to get going is we just use free radical substitution at sp3ch. So that's bromine and light, puts on a bromine, also makes HBr, which we are ignoring. We only have one position here, but once we get to propane, we have 2 possibilities. Of course, this goes for the weaker CH bond, gives us the more substituted position right here. And that's true here, tertiary over primary, and there's only one kind here, so we only get one result here, even though there's 12 different sp3CHs. The methyl, they're all the same, so we only get one product here. We have 2 choices here. It chooses the more substituted and benzylic position, far in preference to the terminal position. So we have all of these bromoalkanes, bromohydrocarbons, and remember all the reactions we had from chapter 9, the SN2 reactions with OH and OR and carboxylates. And, we had a lot of different choices. But one of the choices we had was to do elimination reaction. So if we use T-butoxide with any of these guys except for the bromomethane and the bromotoluene, except for those 2, everybody else is going to give us a pi bond, pi bond, pi bond, pi bond, pi bond. And now, with a pi bond here, we have 2 possible directions we can go. Okay, we can go in the direction that we just talked about. So with HBr and peroxide and light, so notice this is free radical conditions, and these are free radical conditions. They look very similar because they have a bromine in both of them, but they're very different reactions. Okay, this substituted an sp3ch, and this adds to an alkene in a very specific way. Okay, so the bromine will add to the end, and the H will add in the middle. Now we have a whole new class of bromohydrocarbons, a primary. This is the one that I had to give you in the last lecture, but now I don't have to give it to you. Okay, and that could be true here. Now I could do the same reaction here, but you notice I didn't show it. Because if I did this reaction, what I would make is the bromoethane, which we have up here. And we already have a way of making it, so I'm not emphasizing that reaction. That is true down here too. I could use this HBr and peroxide light, and I could make bromocyclohexane, but we already have a way from our starting materials. So that would be kind of a waste to do 1, 2, 3 reactions to make the same thing that we can make in one reaction. So we're not actually showing that reaction here. I can't make a double bond here because I only have one carbon. I could make a double bond here using T-butoxide, potassium T-butoxide. And if I can make the double bond, then we can do the anti-Markovnikov addition and put the bromine at the end, and so now we have another primary bromo compound to play with. So the purpose of all these guys in our course is to give us some examples that we can use our reactions with, but not be out of control as to every possibility in the world. Okay. Now there was one more possibility with these alkenes that we mentioned in our last lecture, and that is we still have an sp3ch at the end here. And so we could come back and do the original reaction, and instead of reacting at the double bond, it'll react at the sp3ch. And so now we have the bromine at the primary position, but we have a double bond that comes along with it, and we call this allylic. Allylic bromo compounds are pretty reactive. You could even say dangerously reactive. And that would be true with this pattern right here. We could put the bromine next to the double bond right here, allylic position. And that would be true with the cyclohexene. We could put the bromine at an allylic position there too. So these are 3 additional guys that we did not have from our starting group up here. We had to make them after we made the alkene. So these have special names, allylic. There are a couple up here. We could make them. This is called benzylic and benzylic, and so they have high reactivity like allylic, but we made them directly. Okay, but I'm just adding them in down here to show you that that special pattern. Now we had one more possibility with our starting guys up here, and that is if we put 2 bromines on, we could eliminate twice and get a triple bond. So that would work here. I could put a triple bond. That would work here. I could put a triple bond. I cannot put a triple bond here because I would have 5 bonds on this middle carbon. I cannot put a triple bond here because the bond angles would be too tight for the triple bond to work. I cannot put a triple bond here because I only have 1 carbon. But I can put a triple bond here. Okay? So those are 3 additional types of compounds we could make if we do 2 equivalents of bromine. Get those leaving groups on there. And then we have to do a double elimination reaction. Instead of using potassium T-butoxide like we do for alkenes, when we're making the alkynes, we use the dialkyl amide, the sodium dialkyl amide anion. We also have to use a 3rd equivalent because as soon as we make the triple bond, it's going to take off this proton at the end, the terminal CH. Okay, because we can't stop it, it's more acidic than the conjugate acid of the base here, which would be the amine. And so we have to come back and do a 3rd step where we work this up or react it. Okay, so this will give us these 3 alkynes that we also have. And those will be potential nucleophiles that we can use with some of these bromo compounds up here. Okay, so just kind of summarized a little bit of some of the reactions, the patterns that we can make. So here's our 7 starting hydrocarbons. Okay, and you might want to go back and look at that slide with all the possibilities in here. Okay, those are all the bromo compounds we can make. I think there's 13 of them. I also gave you 1 ketone. Okay, this would be propanone, but more commonly called acetone. And I gave you 1 carboxylic acid. This is ethanoic acid, but more commonly called acetic acid. And I just gave these as examples to react with some of our compounds down here. After this topic, when we start into our next topic, we'll have ways of making many ketones and aldehydes and carboxylic acids, and that's going to greatly expand the possibilities for you guys, which is a difficult thing, but that's just getting you into the way that organic chemistry works. So that's going to be important for us. Okay, so here's carbon compounds we should be able to make. Okay, remember this is our tool chest right here. We can go here and we can use any of these whenever we want, and from these we'll be able to make a whole lot of possibilities. In our next topic, we'll reduce this number down quite a bit. We won't even give you 7 here. We'll give you a more limited number because we'll have reactions that can make almost any carbon skeleton we want, between all the way up to say C6, C7. Okay, so I'm assuming that you can review and see all these bromo compounds right here. We know that some of these we can do elimination and we can make alkenes. Some we can do double elimination. We can make alkynes. So I have 2 of them here, but here's a third one down here. Now from these compounds, we'll be able to make all kinds of functional groups. So I have here an alcohol. And so when you look at this, what you have to do is try and break this down into how did I join these guys together. So almost all of our topic, except for the chapter 10, free radicals, is nucleophile, electrophile. So when you look at these, you're trying to decide who's bringing the electrons, who's donating the electrons, and who's accepting the electrons, and why are they accepted. Okay, so with a bromine at the carbon, I could bring in hydroxide and displace it, and I would have an alcohol. So that would be SN2. But remember, there's also the possibility of SN1, because that reaction doesn't work real well. That's secondary and tertiary. When we look at an ether, okay, the oxygen's bonded to 2 carbons, so that means we could do it twice. And if we could do it twice, that means there's probably 2 ways we could do it. One would maybe react first on the left side, and then maybe the right side second, or maybe the right side first and the left side second. There's more than one possibility. So there's little breaks here, and that's what you have to be able to think. How do I join these guys together? What's the nucleophile? What's the electrophile? Are the conditions strong or are the conditions weak? Okay, and that's just true for esters too. There's actually 2 ways we can join this ester together. We could join it with the oxygen carbon on the left, or we could join it with the oxygen carbon on the right. And so you want to be able to think through both of those possibilities. We could put a nitrogen there with amines. Okay, remember we had to use azide for that and follow that up with lithium aluminum hydride, and then a workup step. We could put deuterium at any position in there, and that would involve lithium aluminum deuteride. There'd have to be a bromine there. We could put a cyanide there, which would give us a nitrile. There'd have to be a bromine there. Okay, we could join up a triple bond if there was a bromine here. Okay, make the anion of the triple bond and join that up. We know sulfur is a good nucleophile, so we could make a break here, put the bromine at that position. If I have a thioether, or also called a sulfide, we could do it on both sides, just like the ether up above. And so I'd have to have a bromine here, I'd have to have a bromine here. Then we'd have to get into the order. Could it be either side first or second, or is one side preferred to be the first one? Here's another ether. Here's an alkyne at something at both ends. So I could make it a 3-carbon alkyne. I wouldn't need to put that on. I could just add on this 3-carbon group right here. I'd have to have a bromine at the end. So notice that's a 1-bromopropane. Okay, so that would be something like up here. We'd have to do those extra steps. But I could have other groups here. I could have an ethyl or another propyl, and then I would do it at both sides. I'd use some triple bond like this instead of this. I can make an amine. There'd have to be a bromine here. There's a little tricky one here because I have this double bond O, and if I look right adjacent to it, that would be a ketone, a simple ketone, and that's one of the things that I gave you up here, simple ketone. So this would involve enolate chemistry. You have to recognize that this position next to the double bond O could be made into an anion because of resonance, and that means the bromine would have to be here. So you have to come out one step and make your break right here. Esters, remember, could be made on either side of the oxygen, so those are bonds that we could make. And also, if I come over here, I'd have to make, adjacent to this carbonyl group, I'd have to make this bond right here. Here's a nitrile, I'd have to make the break right here. This one we could make from this guy right here, this triple bond, we could make from this guy that's a given. Do a double elimination, or we could just put on one bromine, single elimination. Okay, OHs we just mentioned, OHs, NH2. So all of these guys have key clues, and the clues are almost always the part that's a little different. The oxygen, or the end of the triple bond, or the deuterium, or the NH2. Okay, so those are all possibilities that you want to be familiar with. And on this slide, I did the same thing, except I put in little dashed lines right here, so that these are places where you have to be able to think of how to join these guys together. And, I hope there's a reaction in your mind, but most of these come out of Chapter 9, SN2 type of chemistry, a little bit of SN1 in some places. Okay, so let's take a look at I did a few examples here of target molecules just to try and get you into this kind of thinking. So our real target molecule is down here at the bottom. This is what we want to make from our allowed starting structures. So when you look at that, you go, that looks like a lot of carbons all joined together. But what I see right here, the key clue is this double bond OO. This would have to be from our carboxylic acid. That's the only place where we have an atom like that. And so that would be kind of a small group that we're looking at right there. Okay? So what it means is I probably joined this group up to the end position here, and I joined this group up here either of two ways. I joined it up to the carbonyl, or I used this to attack the carbon over here with a bromine. Okay, so that's the key part that you have to do. And so what we do is we start from one of these parts and work our way backwards. So I see this group right here as something that is added on, and the way I could think of that is if I had a bromine here, because I have a molecule that already has oxygen here, so if I had a bromine here, I could bump it off. So then now my new target molecule looks like this. I have a bromine, and I see a phenyl and two carbons, and then I think back, oh, we had a compound, a allowed starting material that was like that, except now I have a bromine at the end. That was the topic we just discussed. How can I get a bromine at the end position, at the primary position? Okay, I would have to have a double bond. So this would be like target molecule -1, and then how can I do that? So you would have to come up with these conditions. If you can't remember this, then you're just out of luck, because we don't have a lot of choices. A lot of our reactions just have one choice. Well, this brings me to a new problem. Now I'd have to make a double bond. So how do we make a double bond? Well, the way we make it in our class so far is we have a leaving group. Leaving group could be bromine. So if I put a bromine on one of these two carbons, and the easy place is the more substituted one, then I could have this compound. So the question would be, how do I get the bromine off and 1H and make this double bond? And so our way of doing that is potassium T-butoxide. So that would give us our double bond. But now we have a new problem, target molecule -2. So how do we get the bromine on there? Well, I would need, looks like a hydrocarbon, and do free radical substitution at sp3ch. So I could have this molecule, which is one of our allowed starting materials. So all I would need to do is come up with the conditions, which is bromine and light. So that would give us this molecule right down here, which we could then add on to the carboxylate of this guy. Okay. Now if I look on the other side, I have to add on this 3-carbon group, and the bromine would have to be at the end position. Okay, so this is a new target molecule we're looking at. How would I get that bromine on? Well, it's sort of the same strategy we did up here, because it's at the primary position. So I would again need HBr and peroxide conditions to get the bromine at the primary position. Then how would I make the double bond? Well, it's sort of like we just did up here. I'd have to have a leaving group, and then use potassium T-butoxide to make it leave. And then how do I get the bromine on here? Well, I'd have to start with the hydrocarbon and do free radical substitution. So we're allowed to have propane, and then I just have to remember that bromine and light would do that transformation. Okay. So then I come down here, and I have to add on this 3-carbon group that we just talked about to the ester that would be over here. And so I need that ester as a starting material, and I need some way to make this into a nucleophile to get a proton off and have this in an anion. That anion is stabilized by resonance with the carbonyl. Okay, so I use the sodium dialkylamide. So dialkylamide is very capable of taking that H off. And then that enolate then would attack the bromine, displace the bromide, and then we would have this 3-carbon group added on. Okay, so that's how we would do it. But now we'd have to make the ester, and so the joining up here would be at this bond right here. We need the oxygen minus to make it a good nucleophile. We need a bromine right here, and then we could do that. So this is an allowed starting material. Remember, I gave you one acid, ethanoic acid or acetic acid. I'd have to take this proton off. That's pretty easy. I can use sodium hydroxide. And then I'd have to add in this bromo compound to do the displacement and get the ester. And so those syntheses are shown up here. Okay. So this is a moderately complicated problem for where you guys are. It has a lot of steps, but you can see the steps are somewhat repetitive, and there's a certain logic that you have to recognize, and that's the whole point of this problem. Okay, so here's a new target molecule, and notice there's only one oxygen. There's a double bond O, so this probably is not the acid group that we're starting with. This is probably the ketone one that I gave you, propanone or acetone. You can see there's a key bond that's made right here, and so since this is the position next to the double bond O, this is the position where I can make an anion, pull off a proton, stabilize it with resonance. That means I'd have to have a leaving group over here, and so that's the logic that we want to take. So here's my starting material, which is allowed, and then I would need to take off the adjacent proton. All of our enolate chemistry, we use the dialkyl amide to do that. And then I need to put in whatever this pattern is with a bromine at the key position that we're attacking. So in this case, I left out the double bond, so we want to put that one back in. Sorry about that. So then I'd come down here, and I'd say, how do I get this bromine on at this position? Well, that's a sp3 carbon, so I'm going to use free radical substitution. So here's my alkene, and here's my conditions to make the free radical substitution at the sp3 center. But then I have to make the double bond, so how do I make the double bond? Okay, well, I make the double bond by having a leaving group. So the leaving group most logically would be at the more substituted position, and then I would need conditions, which we know are potassium T-butoxide, to make an alkene. Then I have to put a leaving group on. That's a tertiary position. That's the best place to put a bromine. Okay, the weakest CH, most fast reacting, but then I would need the bromine free radical conditions, substitution conditions. And so that would get us to where we want. Okay, that would be the synthesis, except for this double bond I left out. So here's another target molecule, but also I only see one oxygen. So again, this looks like the ketone strategy right here, meaning I have to make this bond right here. We know this is the enolate nucleophile, and so there must be a bromine over here, leaving group. Okay, so here's our ketone. Here's the conditions. Pull off that proton, make the enolate, attack, displace, and add on 2 carbons with the phenyl. Okay, so this is something we actually saw before. I should have come up with a different side chain on there. I wasn't planning too well there. But we know how to do this. We do anti-Markovnikov addition of H and Br at the less substituted position. We ought to make the double bond. That involves T-butoxide and a leaving group over here. To get the leaving group on is our free radical substitution at sp3ch. And so that would get us where we want to go. Okay, so another example. So notice how I'm thinking backwards as I do this. This is a real crucial part. It's not likely you're going to jump all the way back to the start and figure everything out. But if you go back one step at a time, then you know that that was just one step. You have a better chance of remembering what it is. If I look at this one, I'm looking at the nitrile part here, and I'm thinking this is a good place to make a break, because I can buy cyanide out of a bottle, and then if I had a leaving group right here, that would be great. Okay, so that's a good place to make a break. However, if we look a little more carefully, what we see is this is the bromo compound, and that's not one of our carbon structures. We can't make this. Okay, so it'd be kind of stuck. In our next topic, we could make this, but we can't make it right now. So this would be a reaction that would work, because this is a secondary center, but we can't make this bromo alkane yet. Okay, we will, but not yet. So we need a different strategy. So what I did was I came down here and broke the bond here, okay? And I did that sort of for a reason. If I if I broke the bond up here, I'd have a chain of 1, 2, 3, 4. And we don't have any examples where we have 4 carbons in a row. But we do have examples where we have 3 carbons in a row with a leaving group. Okay, so instead I'm looking at this guy right here attacking this guy right here. Since this is the position adjacent to the triple bond, this is an enolate type of center, and I can make an anion here. And that means if I had a bromo here, I could displace it. Okay, so here's our starting nitrile. I'm going to have to take off this proton, and then I'm going to have to attack this position and displace that, and that would give me our target molecule right here. But we don't have this in our tool chest, so we'd have to make this one too. Okay, well, we could make that if I had a leaving group here, and then I use cyanide nucleophile. That would work. So here's our sodium cyanide, and then here's the bromo alkane. So that's a pretty easy reaction that we've seen before. But then I would have to make this bromine at the primary position, but that's just what we talked about. Okay, so I can come along here with the alkene, and I could do the anti-Markovnikov with HBr peroxide. Okay, but then I'd have to make the double bond, and we've done that a number of times. I have a leaving group, so I have to use potassium T-butoxide. Leaving group at the more substituted position means I could start with the alkane, do free radical substitution with bromine and light to get to this secondary bromo compound. So you can see the pathway here. This looks like a nice pathway up here, but we can't make this this hydrocarbon to get started. Okay, so here's another one with the nitrile, again with a little bit of a problem. I could think of breaking it right here, but then I'd have to have a bromine with all this other stuff, and we don't have any compound like that. So you have a choice here. You could either cleave it here, or you could cleave it here. Either way would work. So if I take this one away, I would put a bromine at this position here. We've actually seen that before. And then I'd have to have this nitrile. So how could we do that? Okay, so this nitrile right here, well, I could add cyanide if I had a bromine here, but we don't have any compound that has a bromine right here that I could attack with a cyanide. However, if I break it this way, that would just give me another nitrile and bromocyclohexane, so that would work. For as far as this reaction, I'd have to take the adjacent hydrogen off. Remember, that's because of resonance stabilization of the anion with the triple carbon-nitrogen triple bond. And then here's our electrophile that we added where the bromine is. Okay, I could make a break here using the sort of the enolate strategy again. And if I did that, I would have this very simple nitrile. We could call this ethane nitrile, but most people call it acetonitrile. Okay, so I need to take off the proton adjacent to the triple bond, and then I need my electrophile, which has a bromine where we attacked right here. Okay, so remember, these bring in the electrons. These can accept the electrons because there's a leaving group there, the bromine. Okay, so that means I'd have to make this guy, but this is real easy now because I just have one carbon added to cyanide. So if I had a bromomethane, I could use sodium cyanide, and I would make the acetonitrile. Okay, I would have to make this, but that's just free radical substitution at sp3ch. Okay, using bromine, we're allowed to do that. Okay, so that's going to end this particular topic of chapter 10. We'll start into our next topic, which is a combination of chapter 11 and chapter 12. Okay, look forward to seeing you then.